IT361 Module 4. In this module, first we are going to discuss about vertex colorings. A k-vertex coloring of a graph G is an assignment of k colors 1, 2, etc. up to k to the vertices of G. The coloring is proper if no two distinct vertices have the same color. Thus, a proper k-vertex coloring of a loopless graph G is a partition v1, v2, etc. vk of the vertex set V into k possibly empty independent sets. G is a k-vertex colorable. G is k-vertex colorable if G has a proper k-vertex coloring. We usually use the terms coloring for denoting a proper vertex coloring and k coloring for denoting a proper k-vertex coloring. Next is the chromatic number. The chromatic number, usually denoted by chi of G of the graph G, is the minimum k for which G is k colorable. If chi of G equal to k, then G is said to be k chromatic. This is an example of a graph, particularly a 3-chromatic graph. Next is about critical graph. A graph G is critical if chi of H less than chi of G for every proper subgraph H of G. A k-critical graph is one that is k-chromatic and critical. Every k-chromatic graph has a k-critical subgraph. Next is a statement. Next is a theorem which states that if G is k-critical, then delta greater than or equal to k minus 1. We will prove it by contradiction. If possible, let G be a graph with a k-critical. Let G be a k-critical graph with delta less than k minus 1, and let V be a vertex of degree delta in G. Since G is k-critical, G minus V is k minus 1 colorable. Let V1, V2, etc. Vk minus 1 be a k minus 1 coloring of the graph G minus V. By definition, V is adjacent to G. V is adjacent in G to delta less than k minus 1 vertices, and therefore V must be non-adjacent in the graph G to every vertex of some Vj. But then V1, V2, etc. Vj union singleton set V, etc. Vk minus 1 is a k minus 1 coloring of the graph G, which is a contradiction. Thus, delta greater than or equal to k minus 1. Next is a corollary based on the theorem that we have discussed now. Every k-chromatic graph has at least k vertices of degree at least k minus 1. For proving this corollary, let G be a k-chromatic graph and let H be a k-critical subgraph of G. By the above theorem, which is mentioned as Theorem 8.1, each vertex of H has a degree at least k minus 1 in H, and hence also in the graph G. The corollary now follows since H being k-chromatic clearly has at least k vertices. Next is also a corollary which states that for a graph G, chi greater than or equal to delta plus 1. Next is Brook's theorem. If G is a connected simple graph and is neither an ordered cycle nor a complete graph, then chi less than or equal to delta. For proving that, let G be a k-chromatic graph which satisfies the hypothesis of the theorem. Without loss of generality, we may assume that G is k-critical. By corollary 8.2 that we have seen, G is a block. Also, since 1 critical and 2 critical graphs are complete and 3 critical graphs are odd cycles, we have k greater than 4. If G has a 2-vertex cut set UV, then degree of U plus degree of V greater than or equal to 3k minus 5, which gives 2 delta greater than or equal to degree of U plus degree of V greater than or equal to 3k minus 5 greater than or equal to 2k minus 1. This implies that chi is equal to k less than or equal to delta. since 2 delta is even. Assume then that G is 3 connected. Since G is not complete, there are 3 vertices U, V and W in G such that UV, VW element of capital E and UW not element of capital E. Set U equal to V1 and W equal to V2 and let V3, V4, etc. VV equal to V be any ordering of the vertices of G minus set UW such that each Vi is adjacent to some Vj with j greater than I. This can be achieved by arranging the vertices of G minus set UW in non-increasing order of their distance from V. We can now describe a delta coloring of G, assign color 1 to V1 equal to U and V2 equal to W. Then successively color V3, V4, etc. VV each with the first available color in the list 1 to etc. up to delta. By the construction of the sequence V1, V2, etc. up to VV, each vertex Vi, 1 less than V minus 1 is adjacent to some vertex Vj with j greater than I, and therefore to at most delta minus 1 vertices Vj with j less than I. It follows that when its turn comes to be colored, Vi is adjacent to at most a 1 colors, and thus that one of the colors 1, 2, etc. up to delta will be available. Finally, since VV is adjacent to 2 vertices of color 1, namely V1 and V2, it is adjacent to at most delta minus 2 other colors and can be assigned one of the colors 2, 3, etc. up to delta. Next is a definition of subdivision of a graph. Here, a subdivision of a graph G is a graph that can be obtained from G by a sequence of edge subdivisions. We can see what is a Hajos conjuncture. If G is K-chromatic, then G contains a subdivision of K suffix K. This is known as Hajos conjuncture. Now we can see what is a chromatic polynomial. For any graph G, pi k of G is a polynomial in K of degree V with integer coefficients, leading term K and constant term 0. Furthermore, the coefficients of pi k of G alternate in sign. We can now refer to the function pi k of G as the chromatic polynomial of the graph G. Now, a theorem which states that if G is simple, then pi k of G is equal to pi k of G minus E minus pi k of G dot E, G into E for any edge E of the graph G. Next is about girth and chromatic number. The girth of a graph G is the length of a shortest cycle in the graph G. If G has no cycles, we define the girth of the graph G to be infinite. Given any two integers k greater than or equal to 2 and L less greater than or equal to 2, there is a graph with the girth k and chromatic number L. Next is about one of the applications of the topic, that is a storage problem. A company manufactures N chemicals C1, C2, etc. Cn. Certain pairs of these chemicals are incompatible and would cause explosions if brought into contact with each other. As a precautionary measure, the company wishes to partition its warehouse into compartments and store incompatible chemicals in different compartments. What is the least number of compartments into which the warehouse should be partitioned? We obtain a graph G on the vertex set V1, V2, etc. Vn by joining two vertices Va and Vj if and only if the chemicals Ca and Cj are incompatible. It is easy to see that the least number of components into which the warehouse should be partitioned is equal to the chromatic number of the graph G. The solution of many problems of practical interest, of which the storage problem is one instance, involves finding the chromatic number of a graph. Now, these are some problems for your practice. Try to do it by yourself. That's all from this module. Thank you.